Hi, my name is Hansen and I'm excited to show you my project where I've developed a low-cost OSC-based DAW controller. A DAW is a digital audio workstation which has replaced the old analog workflow of recording a multi-channel recording to tape and then downmixing it to a single stereo recording which is then released. A DAW allows a user to record, edit and then downmix a project entirely on the computer. However, part of getting a great mix is keeping the listener interested and their focus on the correct elements in the mix by adjusting the levels over time. This process is known as automation, where the user creates volume curves for each different audio track. With a mouse and keyboard, this is a time-consuming process, as it can't be done while the audio is being listened to, meaning that changes to the automation have to be listened to, then changed based on experience and intuition, and then listened to again to see if the change matches the expectation. The advantage of what is known as a DAW controller, which is what this project is producing, is that it allows the user tactile control of channels, allowing them to directly write automation data as they're listening by determining when the user is touching the channel and then writing automation data. When the engineer releases his finger from the fader, the DAW stops writing automation data and starts reading it, and the fader displays this level visually by moving in accordance with the automation data. This allows the engineer to not only quickly overwrite changes to automation, but also work on multiple tracks at the same time, and be able to see an overall picture of the levels of each track in the song, and then detecting when the user has released the channel and then reading automation data. The biggest problem with current commercial units is their high cost, the use of proprietary communication protocols that limit their use with different software, and the inability of the user to change and customize functionality according to their workflow. My project addresses these issues by creating a low-cost DAW controller that has a modular architecture that allows the user to change the physical configuration of the device, as well as using the new and highly flexible OSC or Open Sound Control protocol for communicating with compatible software. These three goals combine create a device that has functionality that simply does not exist in the market at the moment, and at the same time hits a new price point, opening up a new section of the market. Current control surfaces also exclusively use an outdated protocol called MIDI, developed in the 80s, which can only send 8-bit integer values to 127 different addresses. This is a severe limitation as it has not sufficient resolution for many controls, and the limit in addresses restricts the functionality that the unit can provide. Alternatively, some units use proprietary communication protocols which add functionality but also reduce compatibility, limiting the full features of the device to only some software. With companies abandoning support for older products, this means that functionality remains limited and may not be compatible with newer versions of the same software. In order to address these problems, the system uses OSC or Open Sound Control, an open source replacement for MIDI which is designed to run over TCP to communicate with the host DAW. This makes it much more flexible to configure. OSC allows many different data types, improving on the limited 8-bit messaging of MIDI. OSC allows floats, integers, strings, all of which are very useful for the project. Also, OSC has no limit on addresses, allowing the messages to be routed based on their content. Thanks to the integration of the OSC protocol and the use of Arduinos as controllers, not only is the functionality improved, but the project is guaranteed to be able to be updated in the future. The Arduinos can be accessed by the user to be reprogrammed. Also, since the device is designed to use OSC as opposed to a proprietary messaging system, it's guaranteed to be compatible with any software that chooses to integrate OSC into the environment. Finally, in order to improve on the modularity of the unit, a flexible architecture was created using the Arduino platform. A single Arduino Uno provides communication via OSC to the DAW. This Arduino formats messages and sends them over TCP. It also decodes messages received by the DAW and decides where they should be sent. Secondly, the fader itself is controlled by an Arduino Nano. The Arduino Nano reads analog values from the potentiometer, implements a control loop, and provides feedback to the motor driver. Additionally, it also uses capacitive sensing to detect whether a user's finger is actually touching the controller. This compartmentalization of the system greatly simplified programming, as it meant that the time-critical aspect of the project could be implemented on a single device. The Arduino Nanos connect to the Arduino Uno over an I2C bus. This allows the master device, the Arduino Uno, to communicate with up to 127 Arduino Nanos, meaning that hypothetically the system could support up to 256 faders. However, the goal of this system was to allow modules with different functionality to be added. Additional Arduino Nanos could be added, but instead of having faders, they could have buttons, switches, rotary encoders, or even small screens. This means that a user could potentially configure their device to have any number of faders, screens, rotary encoders and buttons, or any combination, whatever suits their needs. Most of the learning in this project came from implementing the control loop in the Arduino Nano. Although single-axis movement with DC motors is not a complex problem, the system introduces its own challenges. Firstly, the Arduino Nano only has a 10-bit ADC. This limits the accuracy of the conversion, and the induced quantization noise can reduce the fader's performance, namely making it either less accurate or less smooth. For this project, smoothness is an important characteristic as it makes the faders unobtrusive and quiet. An Arduino Nano is also a relatively slow processor. It also has very little memory. This creates two problems. The speed limits debugging because serial communication to a debugging PC slows down the control loop as much as 50 times, meaning that the dynamics are extremely different. A potential solution is writing the values to memory. However, here a second problem presents itself, that the Arduino Nano can simply not store very much movement of the fader without running out of memory. When experimenting with this, it created a lot of issues with stack overflow and memory corruption that would cause the Arduino Nano to stop executing and for all the data to be lost. The second major problem was making the movement of the fader smooth at low speeds. When a large set point change was made, the fader would smoothly speed up to maximum speed and then slow down, stopping with no overshoot at the target position. However, at low speed, the fader would move in a jagged motion demonstrated here. This can actually commonly be seen in low-end commercial units. An early attempt at the solution involved reducing the proportional feedback coefficient. This smoothed out the response but reduced accuracy, and it was not a great trade-off. I decided that the problem was potentially something to do with non-linearity in the drive mechanism. I realized through some experimentation that the PWM values were not linearly correlated with the speed of the fader. By inputting sinusoids, it was possible to measure this non-linearity in MATLAB, then apply a correction curve, which was then transformed into a lookup table which is stored on the Arduino. The Arduino then can use the lookup table to transform calculated PWM values into corrected PWM values. Ultimately, it was found that the motor had an approximately exponential response to changing PWM values. Ultimately, the combination of feedback and feed-forward correction of the signal was what was used in the final system. A second cause of poor tracking during low speed was also found to be instability in the ADC measurement. It was possible to see by reading ADC values that there were significant amounts of noise being read by the ADC. That exceeded the expected specification given by Arduino. It was possible that this was due to using the internal voltage reference, which combined with high power switching from the H-bridge might cause interference. The idea was to make a low noise voltage reference. This was done by using a standard linear voltage regulator, combined with a very low frequency, low pass filter on the output. This worked exceptionally well and in the best case reduced the noise to significantly less than 1 bit. In conclusion, it can be seen that the key goals of this project have been achieved. A touch-sensitive motorized OSC-based door controller has been created using the Arduino platform, allowing modularity, customizability, flexibility, a low cost, and high performance. In the future, I hope to develop this project into a multi-fader unit. This represents the next step in turning the device from a functional prototype into an actual usable tool. Thank you for watching and being a part of this journey.